All right, today we're pulling back the curtain on an incredible tool that lets engineers and scientists literally see the invisible, COMSOL Multiphysics. We're going to break down what it is, why it's such a game changer, and then, the best part, we're going to walk through your very first simulation, step by step. Have you ever wondered how someone can predict the airflow over a brand new jet wing before it's even built? Or how they can map out the intense heat inside a tiny microchip? Well, they use simulation. It's all about making those invisible forces, like heat or stress or fluid flow, completely visible, turning these super complex physics problems into clear visual results. And that's exactly the world we're stepping into right now. So what is COMSOL really? Well, at its heart, it's basically a super powerful calculator for the laws of physics. It takes all those complicated equations that describe how things in the real world move and heat up and interact with each other, and it solves them. And it does this using a really clever technique called the finite element method. That just means it breaks a huge complex problem down into thousands of tiny, simple little pieces that a computer can actually solve. This is the secret sauce that lets it handle multiphysics, where you have different forces like heat and fluid flow all interacting at the same time. I like to think of it as your own personal virtual physics lab. You can build anything you can imagine, test it under any conditions, and see the results almost instantly, all right there on your computer. So let's dig into what makes this digital lab so incredibly important for modern science and engineering. So why this tool? What makes COMSOL so special? Well, it's this amazing mix of raw power and surprising simplicity. For starters, the interface is graphical and user-friendly, which means you get to focus on the physics, not on writing lines and lines of code. It comes packed with this huge library of physics modules, but the real magic is how easily it lets you link them together. And it doesn't just spit out a bunch of numbers. It gives you these incredible visualization tools to actually see what those numbers mean. And believe me, this isn't just some academic tool. COMSOL is an absolute workhorse out in the real world. It's being used for literally everything, from designing more efficient cars using fluid dynamics, to managing the heat inside the phone in your pocket, to even modeling how medicine travels through the human body. It's the silent engine behind countless innovations we rely on every single day. Okay, so we've got the what and the why covered. Now it's time for the how. Every single project in COMSOL, no matter how simple or complex, follows a really clear roadmap, a set of steps that takes you from a blank screen to a final result. Let's walk through that map right now. This is it. This is the universal workflow for pretty much any simulation you can dream up. I think of it like baking a cake. First, you pick your recipe, that's defining your physics. Then you get your ingredients, which are your geometry and materials. You set the oven temperature, those are your boundary conditions. Then you prep everything for baking by slicing it up, that's generating the mesh. Then you put it in the oven, you hit compute, and finally, you get to see how it all turned out. You analyze the results. See? Every step just flows logically into the next. And you'll navigate this whole process using three main windows. Over on the left, you have the model builder. Think of that as the table of contents for your project. Whenever you click on something in there, the settings window pops up with all the details you can change. And then the big one, the graphics window, that's your canvas. It's where you see your model, your mesh, and of course your final beautiful results come to life. Okay, theory is one thing, but there's no substitute for getting your hands dirty. We're going to build a simulation for something really fundamental, the flow of water through a simple 2D channel. This example is the absolute perfect way to see that 6-step workflow in action. Let's do it. First things first, the project setup. We're going to use the model wizard, and we just have to make 3 key choices. We'll work in 2D since our channel is just a basic rectangle. For the physics, we're going to choose laminar flow. This just describes a smooth, predictable fluid movement. Think of honey pouring slowly, not a raging river. And finally, we'll select a stationary study. That just tells COMSOL that we want to see the final, stable, steady state of the flow, not the messy process of it just starting up. All right, now for the fun part, building the model itself. First, we just draw a simple rectangle to be our channel. Easy enough. Next, we tell COMSOL that this channel is filled with liquid water, which we can just grab from the built-in material library. And then, and this is probably the most important part, we set the boundary conditions. These are the rules of our simulation. We define an inlet where water flows in, an outlet where it flows out, and we tell the software that the top and bottom are solid, no slip walls, just like they would be in a real pipe. We're almost there, just a couple steps left. First, we generate a mesh. This is what automatically slices our rectangle into thousands of tiny little elements. It's how the software breaks the big problem down into bite-sized pieces. And then we hit compute. This is where COMSOL does all the heavy lifting. It gets to work solving the famous Navier-Stokes equations. Those are the fundamental rules that govern how pretty much all fluids move. A few moments later, bang, we have our solution. So we've built the model, we've set the rules, and the computer has crunched all the numbers. But what did we actually find? Let's look at the payoff. This is that magic moment where we turn all those numbers and pixels back into real, physical insight. And here it is. This is our result. When we plot the velocity of the water across the channel, we see this perfect parabolic curve. See how the flow is fastest right in the very center? And then it gets slower and slower until it comes to a complete stop right up against the walls because of friction. This shape tells us everything. Because that parabola, it isn't just some random pretty shape. It is the classic textbook signature of laminar flow. It's the exact profile you would find if you were to measure this in a real-world lab. So, in just a few clicks, we didn't just make a colorful plot. We actually validated a fundamental law of physics. And that is the real power of what we just did. So think about it. We went from a totally blank screen to confirming a core principle of physics. You've just seen the entire workflow from start to finish. We started with a simple water channel, sure, but these exact same steps can be used to model a human heart valve, a smartphone antenna, or the wing of a supersonic jet. The only question left is, what complex world are you going to simulate next?